Okay, so see here. Okay, so we want to go back now and look at the calculus involved with polar coordinates, so the polar coordinate system. And what I want to do is I want to go back and just review with you a little bit about polar. When we talk about, for example, a polar coordinate, what we're saying is, like for example, let's suppose we've got 2 and 2 square roots of 3, something like that. Or actually, that's a rectangular coordinate. Let me put a polar coordinate. Let's suppose I've got 3 and let's say pi over 6. Now, what that tells us is that we start here. It's just like in trig when we had a circle. And we think of a line here, and then we think of a rotation. Like we rotate at pi over 6 unit, or pi over 6 radians. So it's just like in trig, where we have pi over 6 here. And then this 3 here is the length. So we identify this point right here as we get to it this way. We rotate pi over 6 radians, and then from there, from this point right here, which is called the pole, we go out 3 units. And that's how we identify that point. Now, this is in contrast to rectangular coordinates. With rectangular coordinates, we go over so far to the right, horizontally, and then up vertically. So we kind of make a rectangle. Now, you can see why we might use polar coordinates over rectangular coordinates in that if you're talking about things that are circular, like a circle, right? And you talk about points on that circle, it might make more sense to deal with a coordinate system that is more conducive to circles, right? Like this one where you have an angle of rotation and then a distance out. So for example, you could talk about a circle of radius 3 being r equals 3. And it doesn't matter what the angle is. We're saying you always go 3 units from the pole. So what you get then is you get a circle, right? Do y'all remember that? Now, so we might have rectangular coordinates indicating a circle of radius 3, or we could have a polar equation indicating a circle of radius 3. And you can see that the polar looks a lot simpler than the rectangular, because the rectangular coordinates are based on rectangles, right? And we're dealing with circles here. So, intuitively it makes more sense to deal with something that's kind of circular. Now, we have some relationships that we need to remind ourselves of. Let's suppose that, let's just suppose that we've got this r here, right? We've got theta here. And let's suppose that this length right here is x, and this length right here is y. Okay? So here we've got an r and we've got a theta, right? And here we've got x's and y's. So, and I'm trying to identify this point right here. Now, what I'm saying is with rectangular coordinates, we go over this far on the x and this far on the y. So we have this point xy. Now, if we're dealing with polar coordinates, we don't deal with xy, we deal with how much rotation. We deal with this theta. So we would have theta we do r first, right? Whoops, get an eraser. Okay, so we would deal with r comma theta. So we look at how much rotation and how far out. So both of these identify the same point. But look at the relationship here. If we want to find out, well, how are x, y, and r and theta related, well, you can see here that obviously x squared plus y squared equals r squared, right? Just Pythagorean theorem. Okay? And you also know this, that tangent theta equals y over x. Okay? So there's a couple of relationships that we have that are helpful to us. Now, also, relationships that we've looked at before. We've looked at this. We've said, well, sine of theta, remember, equals y over r, and cosine of theta equals x over r, right? Just sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, so we have these relationships. Or another way to look at that is y equals r sine theta, and x equals r cosine theta. Okay? So we have these relationships. Now, I don't want to go back over all that you learned in trig, but are there any questions about these relationships? Okay. So notice, just to remind you about some of these, or how we convert, or how we go back and forth between polar and rectangular, like with equations. Think about this rectangular coordinate system, or this rectangular coordinate circle, the unit circle. And let's suppose we want to put that in polar form. Now, we know this is a circle of radius 1. That's what this is. It's a circle of radius 1. What we can do is we can remember, well, I know that x squared plus y squared equals r squared. So, in place of this, I can just put r squared. And then I've got a 1 over there, nothing to do with that. Take the square root, and I get r equals 1. See? Everybody see that? So we could either describe a circle rectangular with rectangular coordinates, x squared plus y squared equals 1, or r equals 1. And r equals 1 just seems much cooler, right? Any questions about that? Now we can have others. Let's look at other types of equations that we could have. What about this one? Let's suppose we have x plus y equals 1. Something like that. Well, what is this right here? What is this? Just rectangular coordinates. What is that at the graph of? Yeah, it's just a line, right? So think about this. I might say, well, I don't know what to do here. Well, one thing I know is I can replace x with r cosine theta, right? And I can replace y with r cosine theta. See, there's nothing wrong with what I did because that's a true statement, right? X does equal r cosine theta, and y does equal r sine theta. So now, if I wanted to have this equation as r equals something, and typically that's what we're going to do. We want it r equals something if we can. I just factor out an r. See? And then I divide. Now, take a moment to just dig what happened here. We've taken this simple equation for a line, x plus y equals 1, and now we've got this thing. So maybe x plus y equals 1 is a simpler way, right? Because it's a line, right? It's not a circle. So modeling a circle, it was easier to use polar coordinates. With a line, not so much so, right? Y'all see that? Okay, so this r equals 1 over cosine theta plus sine theta, that's a line. X plus y equals 1, same line. Okay, does everybody see that? Now, let me ask you this. What about y equals x? That's a line that just diagonal, right? Cuts right up through the origin. And let's just graph it a minute. Let's see what we got. It's just something that looks like that, right? Now, what is this angle right here? What is that angle? Yeah, let's do pi over 4. Just because we're in calculus and we're used to dealing with radians. So we'll do pi over 4. But 45 degrees, that's right. Okay, look, what we've got is we know that this y equals x and this line right here are the same, right? Now, let's think about this concept. If you were going to graph something like y equals 3, what is that? It's just a horizontal line, right? You notice it doesn't have an x in it. That's because y equals 3 doesn't care what x does. It's just a horizontal line. Well, the same type thing applies in polar, where we could say this, theta equals pi over 4. And that says, no matter what r is, theta is always pi over 4. So no matter what point you have out here, no matter what point, theta is always pi over 4. So this right here, theta equals pi over 4 and y equals x, that's that line. Now look, huh? Yeah, let me show you what happens here. Let's suppose, so let me just go ahead and convert this. Let's suppose we didn't make that observation. Let's divide both sides by x. Okay, so I've got y over x equals 1. Now remember, y is r sine theta. So this is r sine theta, and x is r cosine theta equals 1. And that means tangent equals 1, tangent theta equals 1. Now there, that's the polar form of that y equals x. But another way to say that is theta equals pi over 4, right? So we could say that. Yeah. Now look, remember when we talk about graphing polar, one of the things I also want to draw your attention to is this, that because this problem kind of brought this question up. Remember, if you've got something like this, let's suppose you've got 3 comma pi over 4. And let's suppose we've got negative 3 comma pi over 4. Now notice both of these are on this line, theta equals pi over 4, right? This is a point on that line, and this is a point on that line, right? The r is just different. Now, do you remember what is the difference when you have 3 and negative 3, and you're going to plot those? What is the difference?
One, you start on the positive x-axis, and the other you start on the negative x-axis?
Well, here's what happens. 3 pi over 4 is right there, right? You rotate up pi over 4 and you go out 3. When you think of the negative part of that, what you would do is you would just reflect it right over this pole, right? Another way you could do it is you could think, well, that same point would be this, 3 and pi over 4 plus pi. In other words, you could change that negative 3 to a positive as long as you had pi to the pi over 4. Because the point is, it's reflected across this origin. So when you see that negative r and a positive angle, you're just ignore the negative altogether. Plot the 3 comma pi over 4 and then just shoot it right across the pole. Do y'all see that? So when you see that negative, and that's what it means. That's how you interpret it. Okay, does that ring a bell? Back when you were very, very young in trig? Okay, any questions about that? Does everybody see how that works? Now, what do you think about this? Let's look at another one. What do you think about theta equals pi over, well, no. What would that be in rectangular coordinates if you have theta as pi over 6? What kind of shape is it? Yeah, it's a line. And it, yeah, and instead of the angle being pi over 4, it's pi over 6. Now, so it's 30 degrees. So you could say, well, tangent of pi over 6, remember it's y over x, right? And tangent of pi over 6 is 30 degrees, right? Did I say that? I thought I might have heard myself say 60 degrees, but it's 30 degrees. So this is going to be 1 over the square root of 3. So you have 1 over the square root of 3 equals y over x, or just do y equals 1 over the square root of 3x. There you have it. That's your line. See, because theta equals pi over 6, it doesn't care what r does, right? Theta is always pi over 6 for whatever r you give me.
Could we turn that into parametric and just, since it's a proportionality, say y equals 1 and x equals the square root of t?
Yeah, you could. You could parametric, yeah. You could go to parametric. You could, definitely. You could say, for example, in this one, you could let x be t and y equals 1 over the square root of 3t. You could parametricize it that way.
I was just thinking, since we have y over x equals 1 over the square root of 3, if you let y equal t, then x would equal the square root of 3 times t.
Oh,
Since it's just, never mind, I don't know where I'm at.
well, no, we can explore that later. Yeah, I got you. Any other questions or observations? Okay, now, what I want to do is I want to just go back and remind you about when we have a function defined this way. Let's suppose that we have this. Let me just do a sine. Okay, and let me make this a 4 sine theta. Now, I'll just make it a sine theta, okay? A sine theta. Okay, let's suppose we have that. Now, this is a function. And what I mean, r is a function of theta. So no matter what theta you give me, I get exactly one value of r out. Now, if you look at the graph of this, it's not going to pass what you would call a vertical line test. But that's because we're not dealing with y being a function of x. We're dealing with r as a function of theta. And whatever theta you give me, I get out exactly 1r. So every input gives you exactly one output.
Is this the one that forms like the rosette?
Not this one. Not this one. Let's take a look and see what this does. And let me show you. Now, if I had put like sine 2 theta in there, or 3 theta, I think that's what you're thinking about. Yeah. Okay. Now, let's just look at this simple one here. Okay? So I'm going to look at some values of theta, and then we'll look at r. Okay? And I guess what I'll do is I'll look at 0, pi over 6, pi over 4, pi over 3, and pi over 2. Let's do that. Okay, now, I want to show you what happens here. And I know what this graph is already, I know what it's going to look like. So let me just go ahead and graph it here. Actually, move this down a little bit. Okay. I tell you what, let me go a different route. Okay. Now let's suppose, let's suppose that I want it to, now this is what that graph looks like, y equals sine x. Let's suppose I have the pole right here, okay? And let's suppose that I put in a 0. Well, if I put in a 0, r is equal to 0, okay? So I just get a 0 right there, right? Now let's suppose I put in a pi over 6, then r is equal to 1/2, right? Now, so what this is, we're saying that when you have the angle pi over 6, this length here is 1/2, okay? Now, I put the circle here in advance to help myself to make these lines look reasonable. But notice this is supposed to be a 30-degree angle, and this length here is 1/2. Okay? That's what r is. Because what I'm doing is you give me a theta, and I'll give you the length. I'll give you r. Now, if we put in a pi over 4, what do I get? I get the square root. Whoops. I get the square root of 2 over 2, right? And then, if I plot that, it's going to look something like that, right? Okay. Now notice, so r is getting a little longer, right? Now, if I put in, Let me go back and put in this one. Pi over 3, I get square root of 3 over 2. Go back, get this. Goes up like that, right? Okay. Now, act like the circle's not there. I'm just trying to show you. If this particular graph will form a circle, r equals sine theta. Now, if I put in a pi over 2 is going to give me 1. And, of course, sine of 1 is right up there. Now, if we continued this, and I went, if I went to the next one, like 2 pi over 3, and 3 pi over 4, 5 pi over 6, and then finally pi, what I would get is this circle. Okay? Yeah. Well, yeah, what you would have is it traces out a circle is what happens. Okay? Now, what if this had been r equals 4 sine theta? What would this length right here, this one right here at pi over 2 be? Okay? It would be, right, it would be 4. Now, you take note that the radius is half of that, right? So it makes a circle up here, and what this number out front would give you is the diameter in this particular graph, right? So this particular circle has a radius of 1/2, doesn't it? See that? Okay. Now, let's just explore this a second. Let's look at this because these are just some familiar things we can keep in mind. Let's suppose we have a sine theta. That is a circle that looks like this. It's up here like this. And the radius, the radius of the circle is 1/2 a. Okay? So a is the diameter of the circle. Y'all see that? Now, if we did this, if we did r equals a cosine theta, what do you think that would look like?
It'd be one centered on the x-axis.
Yeah, I think both of you were saying this. It looked like that.
Yeah. And if you add them, and if a is like a value like greater than 1, it becomes dimples, kind of.
Yeah, you can, yeah. Okay, so you see this. So you see how these graphs are formed, right? Formed back, when you were dealing with, polar and trig. Any questions about this? Now, of course, what we want to do is we want to learn how to apply some calculus to this. Okay, any questions? Okay. Now, so here I've got r equals sine theta. And I want to find dy dx. Okay? So here's my objective. I want to find dy dx. Now, if I wanted to find dr d theta, just straight up differentiate, right? But I don't want to find that. I want to find dy dx. I'm not finding the derivative of r with respect to theta. I'm finding the derivative of y with respect to x. But it's all, there's no x and y up there, right? Not obviously, right? It's buried in there. So we want to figure out, well, how do we get at that? How do we find dy dx? Well, remember this, that x is equal to r cosine theta, and y is equal to r sine theta, right?
So if you multiply both sides by r.
Well, think about this though. In this case, we have an r, don't we? R is equal to sine theta. So what we're going to do is we're going to transfer this. We're going to convert to parametric because we know how to find the derivative dy dx in parametric. So here's what we have to do. We're going to do this. We're going to say, okay, x is equal to r cosine theta. Well, this is sine theta cosine theta. See? Because this right here, whoops, this right here is r. Whoops. Actually, what did I do? I meant, yeah, I did it. This is r, right? Right? X is equal to r cosine theta, and
Wouldn't that be sine over y? I don't get.
well,
Oh, never mind.
see, so I've got my r right here.
Yeah.
And I know that there's this relationship that we learned about earlier that x is equal to r cosine theta. So let me take the r that I was given, sine theta, and put it in front of that cosine. Now, y, on the other hand, is sine.
So wouldn't that be r squared?
Hang on just a second. What now?
Wouldn't it be r squared?
Well, what we're saying, okay, so this right here,
Yeah.
this r right here, here's that r.
Okay, so it's a different r and the y?
Yeah, what we're saying is there is this relationship, r equals sine theta, and r is defined to be sine theta. So we have this curve, and r is ever changing, right? So you give me a theta, I'll give you an r. Well, what is r? Well, r is sine theta. So if I know that x is r cosine theta, I will just replace the r in r cosine theta with sine theta, which is what it is.
And for, I guess for y, so you'd write that as either sine theta squared or r squared?
Yeah, this one right here. So here's what we have. This one is y equals sine squared theta. Do y'all see that? Any questions about that?
That would be equivalent to r squared, right?
Yes. Okay. Now, remember, we know how to find dy dx, right? dy dx is equal to dy d theta over dx d theta. Right? Do y'all remember that when we did the parametrics? Okay, so I'm going to differentiate the top. 2 sine theta cosine theta. Everybody see that? I differentiated dy d theta. Okay. Now I'm going to come up here and do the dx d theta. So the dx d theta, we could mess around with this and get an identity, make it a little cooler, but let me just use the product rule in this. The derivative of sine is cosine. Okay? Plus, the derivative of cosine is negative sine, so this is this one, right? Okay? Everybody see that? Did I do that right? I just used the product rule. Now, let's take a minute and see what we have. Oh, look, the top, I could rewrite that as sine 2 theta, right? Sine 2 theta. Now, what about the bottom? Is there any way I can rewrite sine, cosine squared theta minus sine squared theta? Can I get a witness?
No, not one.
No, if it were plus, it'd be a 1. Okay, so what is cosine squared theta minus sine squared theta? Yes, cosine 2 theta.
Oh, yeah.
That's it. Okay, now, so is there a way I could write that a little cooler? Yeah, maybe tangent 2 theta. Okay, does everybody see that? So look, remember, what our objective was here, it was to find dy dx, right? I was not trying to find dr d theta, right? So there's a difference. I was trying to find dy dx. Now, if I wanted, let's suppose, let's look at another one here. Let's suppose I have this one. R equals, let's say 1 plus cosine 2 theta. So if that's what R is, and we want to find dy dx, How would we do that? What would the x be and what would the y be?
Okay, so it'd be 1 plus cosine 2 theta times cosine,
Okay?
and then 1 plus cosine 2 theta times sine.
Yeah, there you go. And then, you would just do the nuts and bolts of the, jump in there with your algebra and your, right? So look, all that we learned about parametrics, we're applying to this. Notice we're just transferring over. Okay, any questions about that? No questions? Okay, I think what we want to do then is we want to... Okay, now let's suppose... Let's look at a situation like this. Let's suppose we've got r equals 1. Now that's a circle, right? Okay, everybody look. This is a circle. And let's suppose that I want to calculate the area inside this circle. Now we already know how to do this. We know pi r squared. So the area inside this circle is just going to be pi, right? No, this won't be related rates. So look. Let's just think about this circle that we have here. And I'll just draw it out. And let's suppose, I'm just going to, we've got this r equals 1. This is in polar coordinates. And let's suppose that I want to calculate the area of the circle, but I want to kind of do it in a roundabout way. In fact, what I want to do is I want to just get a wedge of this circle right there. Okay, there's a wedge of it. And I want to calculate the area of this circle using calculus techniques, calculus concepts. So what I have here in between this little angle here, let's call this angle delta theta. Okay? Y'all see that? I've just got delta theta. In other words, it's the change in theta, right? I go from this angle to this angle, right? So let's just call that delta theta. Now, what I want to do is I want to calculate the area of that little wedge, right? Now, just in general, if you think about the area of the wedge of a circle, wouldn't you take the angle, in this case delta theta, and that's a fraction of 2 pi, right? Because remember, all the way around the circle, if you go all the way around the circle, you have 2 pi radians, right? Well, this delta theta is not 2 pi. It's a fraction of it, right? Okay? So this right here is a fraction of that circle. Now, the whole area of the circle is 2 pi r, isn't it? I mean pi r squared. I'm sorry, pi r squared. Okay. Isn't that the whole area of a circle, pi r squared? So wouldn't this right here altogether be the area of that wedge? Because it's the fraction of it, isn't it? If pi r squared is the area of the whole circle, then this multiplied by this, that's the fraction. So if this were 90 degrees, I would say, okay, 1/4 of pi r squared, that's my first quadrant area, right?
Can we just say delta theta over 2 times r?
Yes, sir. Let's do that. That would be better, wouldn't it? So it looks like what we have here is these pi's cancel, and you have delta theta, let's do a nice yellow, delta theta over 2 r squared. Now, that right there is going to be the area. I realize the area of this one is 1. But let's just, you give me a radius and you give me an angle, the fraction of the circle, and I can tell you the area of that wedge, right? Now, this is one wedge of the circle. You remember, and let's just consider this delta theta to be infinitesimally small, right? And then let's break this circle into lots of wedges, billions and billions of wedges with all these little delta thetas. So we're getting all these area of wedges and we want to add them up. So it looks like what I would do is I'm going to add up all these things, and I do it with this superpower that I have called the integral, right? And what I want to do is I want to integrate from 0 to 2 pi. And it's going to be 1/2 r squared delta theta. Or, d theta. Right? If we use sigma notation, we would have the delta theta and so forth. But you can see what we're doing with this integral. We're adding up infinitely many of these infinitesimally little small wedges, right? Okay? So we're adding up this wedge, which has this area right here. And we're adding up all of them from 0 to 2 pi. So just let theta be from 0 to 2 pi. Now, let's integrate this. Let's see what we get. When we integrate this, we get 1/2 times 1/3 r cubed from 0 to 2 pi, right? Is that right? Wait a minute. No, that's not right. I'm integrating with respect to theta. Ooh, you've got to watch yourself. You got to watch. You got to pay attention. And you know what? I've got to pay attention. I'm integrating with respect to theta. Don't fall into that trap, right? So look, from now on, you pay attention to what you're integrating with respect to, right? I'm integrating with respect to theta. So the integral of r squared is r squared theta. You see that? Yeah. So you're integrating with respect to theta, not r squared. Now let's see what we've got. So now let me go through and integrate this. Now let me go through and finish this off. So I've got 1/2. Now I've got r squared times 2 theta. 2 theta. Now I realize my radius is 1, but let me just carry this along. Minus 1/2 times, r squared times 0, right? Just to remind us about the fundamental theorem. So what do we got here? We've got the 2's cancel, and we've got pi r squared. That's the area of a circle, right? Now, if I had replaced the r with 1, we would just have pi. But do you see that? So what we did was we computed the area of the circle by adding up these infinitely many things. Now look.
No, we did not just derive it.
Look, let's suppose we don't have a circle though. Look, let's suppose we have this curve. Okay, look at that curve. And we have this function, r f of theta. Let's call it f of theta. Because it could be sine theta, whatever. I mean, not with this curve. But let's just suppose that we have this curve, r equals f of theta. And we want to find this. We want to find the area of some region here. Okay, so this is alpha, and let's suppose this is beta, right? We want to find the area from here. So we're trying to find this. We're trying to find this area right here. So it's not a circle, but we're going to use the same concept. So dig this. I'm gonna get all of these little things. Okay, look at that. I've got a little wedge here, right? And this little wedge here has a delta theta in it, right? Okay. Now notice that it's not exactly, it's not exactly the area I'm looking for, right? I mean, it doesn't go out here perfectly, right? In other words, it doesn't perfectly fit the curve like it did in the unit circle. I mean a circle, right? So there's a little bit of error, but remember, we're letting this delta theta get infinitely small, right? You remember how we introduced integration with area under curves? And we had rectangles that were not exactly, right? When we introduced integration, we had rectangles. And remember, the rectangle had a little bit of overhang sometimes. Sometimes it'd fall short of the true area. But what we did was we let the width of the rectangles get infinitely small. And then we added up all those areas. Well, that's what we're doing with these wedges. We're letting delta theta be infinitesimally small, right? And we're adding them up. So what we have is we go back to this formula, right? 1/2 r squared d theta. Okay? So what we do is we say, okay, I'm going from alpha to beta, and I'm going to do 1/2 f of theta squared. This is how we would calculate the area. This is your formula. Whenever you have a situation where you're trying to use polar and you're trying to integrate, you're always going to do 1/2 whatever r is squared. So for example, let's go back to this one. Let's suppose we have sine theta. And I want to get the area of that circle. Okay? I want to get the area of that circle. Now, remember we said it looks like this. So here's what I'm going to do. I'm going to do 1/2 sine squared theta d theta. And I could go from 0 to pi. I could do that. But maybe I would rather go from 0 to pi over 2 and just double my result, right? Because there's symmetry there, right? In other words, I'll get this part. I'll get this part here and then just double it. Yeah. Okay, any questions? Now, this is how we set up. Notice we always have the starting point of 1/2 r squared, and we have to establish our bounds of integration. Yeah, you're only going to find this area, but I'm doubling it to make it easier on myself, right? I'm using symmetry. So actually, it really doesn't make it that much easier on me. I could go from 0 to pi. If I go from 0 to pi, that's the same as 2 going from 0 to pi over 2. So if we do that, then notice what we have. This 2 gets rid of that 1/2, which that's not too big of a deal, actually. But now, I'm going to replace the sine squared. How do we integrate that? Do you remember how to integrate sine squared? Well, remember it goes like this. 1/2 minus 1/2 cosine 2 theta. Do you remember that? The power reducing formula? Okay? That's something we did a while back. Okay? Now we go ahead and integrate that, and we get 1/2 theta minus 1/4 sine 2 theta. And I'll go from 0 to pi over 2. Okay? Then if we plug all of that in, right? If I plug in everything, I'm just going to get pi over 4. Am I? Is that true? If I put in a pi over 2, yeah, I just get pi over 4. You can go ahead and work it out, but that's what you'd get. Any questions about that? No questions? Okay, now,